Look at this expanding mycelium network. These are dermatophytes, parasitic fungi that are structurally simple, yet notoriously capable of surviving aggressive medical interventions. There is a remarkably high clinical failure rate when using traditional topical antifungals, which is strange given the organism's baseline vulnerability. We have to examine this cross-sectional diagram of the human nail unit. You can clearly see the distinct layers, the nail plate on top, resting on the nail bed, with the nail matrix tucked at the base. The dermatophyte entrenches itself deeply within the nail bed and the matrix, using the overlying structure as a hardened bunker. The primary obstacle protecting this bunker is the keratin plate. It is a highly cross-linked, tightly bound biological shield. Conventional, water-soluble medications physically cannot penetrate this dense keratin lattice. Getting rid of the infection requires a sequential, multimodal biochemical protocol. We must systematically dismantle the barrier before attacking the organism itself. Without first engineering a mechanical breach of the keratin, any fungicidal attack is physically blocked at the surface, while the fungus thrives below. The first phase of this eradication cascade is to artificially plasticize the nail. This is achieved using a high-concentration urea compound, specifically around 40%, which acts as a keratolytic agent. Infected nails are structurally rigid and often thicken considerably as the fungus forces layers of keratin apart. This microscopic cross-section shows how the compound attacks rigidity. Concentrated urea molecules penetrate the tightly bound keratin matrix. Inside, urea breaks the hydrogen bonds holding the strands together, softening the impenetrable fortress and transforming it into a highly permeable mesh. Urea is not a fungicide. It functions solely to dismantle the physical barrier and grant access to the infection site. Bypassing the bioavailability barrier through this keratolytic disruption is the only way to deliver lethal agents to the deeper infection sites. With the keratin mesh now permeable, we can initiate the first aggressive chemical attack. Dermatophytes have strict environmental requirements. They require a neutral to slightly alkaline habitat to survive. We can radically manipulate this localized environment using highly concentrated acetic acid, such as apple cider vinegar or vinegar essence. Acid molecules flood downward through the micro fissures in the keratin, dropping the localized pH from 7.5 to a highly acidic 3.0. This sudden drop causes severe trauma via denaturation. Vital fungal proteins violently unfold, losing their three-dimensional structure and biological function entirely. Without these functioning proteins, the mycelium is paralyzed, preventing any further spread of the spores. This radical shift in pH destroys the stability of the environment, rendering the habitat physically incompatible with fungal life. Now we transition from environmental manipulation to a direct, targeted assault on the fungal cells. There is a secondary pharmacokinetic hurdle here. Water-based acids cannot cross the deeper lipid or fat layers, protecting the fungal cells. This requires lipophilic or fat-soluble agents. The most potent option is carvacrol, the active compound found in oregano oil. By pairing carvacrol with a heavy carrier oil like castor oil, we ensure a slow, deep diffusion through those lipid barriers. This animation shows carvacrol's lethal mechanism of action. The molecules physically wedge themselves between the lipids, tearing visible perforations in the fungal cell membrane. This structural damage causes a catastrophic osmotic imbalance. Intracellular contents leak out, triggering unavoidable cell death. Utilizing these specific organic compounds allows for a mechanical dismantling of cellular architecture, an attack against which fungi cannot evolve resistance. The final vector of attack moves away from topical application entirely, relying instead on systemic, internal delivery. This phase uses allicin, a highly reactive sulfur compound derived from crushed garlic. When ingested in high doses, allicin is absorbed into the bloodstream and transported directly to the deep capillaries of the nail bed. In this cross-section, a pincer movement takes shape. Sulfur compounds travel upwards from the capillaries, converging with topical treatments moving downwards. At the infection site, allicin blocks the metabolic pathways necessary for energy production, completely halting new cell wall synthesis at the deepest anchor point. By choking off metabolic function from the inside out, the infection is starved precisely in the areas where traditional topical medications fail to reach. In this macro view, we see the result of this synergistic cascade. The fractured surface rapidly regenerates, pushing out impurities, until the biological structure is entirely clear and solid. The sequence here is rigidly dependent. Urea must breach the physical barrier. Acetic acid collapses the environmental pH. Carvacrol must perforate the lipid membranes, and allicin must sever metabolic synthesis. The absence of even a single phase allows the biological fortress to remain standing. This is why singular treatments almost always fail. A blunt force approach with a single pharmaceutical agent cannot overcome the nail unit's complex architecture. Permanently eradicating persistent pathogens requires understanding their structural vulnerabilities. Clinical success relies on precision biochemistry rather than sheer pharmacological force.